Hello, my name is Rob Reynolds. Welcome to Business Calculus. Today we're going to be looking at section 2.3, rates of change, and remember the velocity is the first derivative, and marginal, we're going to find out marginal revenue, marginal cost, and marginal profit are all rates of change. And a rate of change is nothing more than the slope, y minus y over x minus x, slope of the tangent line, which we know now as the derivative. So the average rate of change is a little bit different than the instantaneous. The average would be the secant line, so the average rate of change would be the slope. And then if I push that line to those 2 points closer and closer together, I'll get the instantaneous rate. Let's see if I can grab this and show you. So those points get closer and closer together, and then that'll create the instantaneous rate or the tangent line. So marginal revenues, marginal costs, and marginal profits are all rates of change. So we know from the previous sections the rate of change is this formula, but we're going to be using the cheat way to find the derivatives this time. So remember, slope and rate of change is the same. Velocity is the first derivative. If we talk about acceleration, I need the second derivative. And when determining the rate of change, be careful if they're asking the average rate of change or the instantaneous rate of change, because we're going to be figuring those two separately. The difference again would be this is just given 2 points, and it's just y minus y over x minus x. But this would be 1 point, instantaneous at a point, and I can find that point if I push those 2 points closer and closer together, and then all of a sudden there's no distance, that's delta x, no distance between the two, and then that would be the tangent line. So if I keep drawing and there's no distance between, then I'm tangent to the curve. So I think you know these definitions by now. Average rate of change. Average is again 2 points, the secant. The average velocity, which is another word for speed. It's common with miles per hour. The change in distance over change in time. So if you have an object that's falling, and it starts up at 100 feet, we can find average velocity between 2 times, and we'll look at the intervals between 2 times. So here's my formula, and I'm going to say find the velocity between 1 and 2 seconds. So the average would be, don't take the derivative of this, the average velocity would be f of 2 minus f of 1 all over 2 minus 1, which is 36 minus 84 over 1, which is negative. The negative just tells you that it's falling, negative 48 feet per second. And then you could repeat that process for part B and get 64 minus 84 over 1.5 minus 1, which is negative 20 over 0.5. You can see I'm getting a little bit more accurate. So instead of negative 48, I'm at negative 40. And then if I were to push these 2 points even closer together, remember we're getting closer and closer to the instantaneous rate at just 1, which I'll show you in just a moment. But if I evaluate the function at 1.1, so I'm just going to plug this in at 1.1, I always think the easiest way to evaluate is to go to your calculator. I'm going to trace it so I can see the function. And if I evaluate it at 2, I can see I'm at 36 and 1. If I evaluate it at 1.5, this is how I'm coming up with the numbers really fast. So if I want to evaluate it at 1.1, you can see I'm at 80.64 minus 84 all over 1.1 minus 1, which is negative 3.36 over 0.1, which is negative 33.6 feet per second. So I'm getting closer and closer. See how these points are getting closer and closer together? So if I keep pushing that, then I will eventually have evaluated the instantaneous rate. And the instantaneous rate would be, well, all I have to do is find the derivative of this function. And the derivative would be negative 32t. Watch my previous lessons on how to do that, the short method, without actually using the limit process. But then if I evaluate h, the derivative at 1, you can see it's negative 32 times 1, which is negative 32 feet per second, which I'm really close because these points are really close. But as I get closer and closer, and push that secant line to the tangent line, I get the exact velocity. So the average velocity, here's how the author chose to work this out. I think we ended up with negative 33.6 as well. And then the instantaneous, we're pushing the secant line to the limit, which means take the derivative of this. You could always do this through a table setup to find that it's negative 32, but I like our method a little bit better. Take the derivative and evaluate the derivative. So remember, instead of doing this f at x plus h minus f of x all over h, we're going to use the cheat method for the derivative, unless it says use the limit process. So the general position function for a free-falling object is negative 16, this t squared. This negative 16 has to do with gravity, the initial velocity, v sub o, and the initial height. And then t, of course, is the time that passes. So the derivative of that would be negative 32t squared plus the initial velocity. So I have a diver that's going to jump from a diving board, and his initial height is 32, so we'll put that as the h term. Notice that his initial velocity must be 16, but the question says, when does the diver hit the water, and what is the diver's velocity? Well, let's find out when the diver hit the water first. The diver is going to hit the water when this function hits 0. And it'll probably hit 0 twice. We'll explore both those answers. So all we need to do is set the function, negative 16t squared plus 16t plus 32. We'll set this equal to 0. I'm going to divide everything through by negative 16. That will just make the number smaller, a little bit easier to factor. Factors of 2 that differ by 1 are 2 and 1. Signs are going to be different, so t minus and t plus. But of course, t can never equal negative 1, so I'll throw that answer out because time can't be negative. Here it is, time is 2. So it takes 2 seconds for this diver to hit the water. So to find the velocity, how fast he's going, all I need to do is evaluate the derivative, which is the velocity function, at the time of 2 seconds. So the first part is I found out that it takes him 2 seconds to hit the water. Part 2 says, let's go find the velocity at the time that he hits the water. So the first thing I need to do is find the derivative here. So the derivative is negative 32t plus 16, and then evaluate that. Negative 32 times 2 plus 16 should be the velocity. The negative tells you, again, that he's going down, and negative 48 would be the velocity at which he's traveling. So we got after 2 seconds, and negative 48 feet per second is what we had as well. So again, notice this is just saying, hey, notice that the initial velocity really was 16. Rates of change in economics. You guys are business majors, perhaps, so we're going to be looking at marginal revenues. You already know that a capital P is profit. We'll just have some definitions here. But a small p is going to be the price. So those are kind of confusing because my capital P's look like my small p, so be careful. We should try to denote this a different way somehow. The small p and a capital P. So be careful. There's two P's floating around here, price and profit. But the profit is your revenue minus your costs. Your revenue is the money that's coming in, and if you subtract out the money that's going out, or your setup fees for costs for the building or the electricity for your bills and for your laborers, after you deduct all that for your revenue, the money coming in, that's called profit. So the derivative of the profit, revenue, and cost are called marginal profits, marginal revenues, and marginal costs. Now remember, marginal just means slope. It's the change in the total cost if you increment by increments of 1 unit. So I'm going to increase the marginal cost by 1 unit, and then I'll have 2 points, and I can find slope. And remember, whenever you're finding slope, that's the rate of change in the total cost, and that's the derivative. So again, in economics, if you add 1 unit, that's going to be the slope of the tangent line. So your marginal cost is your slope of your total cost, and the marginal revenue is the slope of your total revenue. So in the real world, usually we're talking about units produced and sold are just integers. You're probably not going to produce the square root of 2 t-shirts, although we could, but usually we're integers. So I'm just going to pretend to connect this together for the purpose of a continuous function, and remember, the points in between may not make sense, but in order to write a function, we'll connect the dots. Once you have a function, we can go ahead and find the slope at any given point. Marginal revenue, we can find the maximum and the minimum costs. So an example of this would be the profit function is given for selling X amount of alarm clocks, and we could find the marginal profit for the production level at 50 units, and then compare that marginal profit with 50 and 51, which the actual gain in profit of just increasing it by 1 unit. So for the solution for that, we need to find the derivative, because remember, whenever you see the word marginal, that means go find the derivative. And the shortcut way to find that derivative is 3 times that 2, which is 6, and the derivative of 10x is just 10. So the derivative is 0.0006 x squared plus 10. So if you evaluate it at 50, instantaneous, the marginal profit, you can see, would be $11.50 per unit. So there was a second part to this. Now, the first part just said find the marginal profit for 50 units. Compare the part B says compare the marginal profit with the actual gain in the profit obtained by increasing the production level from 50 to 60. So what's happening here is now we're going to look at the actual profit. So instead of looking at the derivative, we'll just look at the actual profit and compare the profit at 50. So P sub 50, I'm going to plug 50 in right here for X, so 0.0002 times 50 cubed plus 10 times 50. Find that answer, which I believe is around $525. Compare that with increasing it with 1 unit, which is the same thing, but just change this 50 to a 51. I would suggest just going to your calculator and typing it in. So at 51, just rounding it off to the nearest penny is $536.53. But then look at the change here. If you subtract the difference, it's around $11.53, which is pretty much what we had for the marginal revenue. We had $11.50, so it's a great approximation because, again, here's how the author chose to do it. So good, $11.53 is what we got as well. So you can see that's really close to what we had, 1150 and 1153. So this is a great way to approximate. Instead of evaluating each one, we just find the derivative and do the instantaneous. The example that we just explored is really kind of unusual because it was just continually increasing. And most often we have things that increase, and then once it reaches so much demand, it'll start to decrease as well. So a little bit more realistic example in rates of change of economics is to look at supply and demand. Your price per unit, remember your price is a small p, be careful that's not profit. So if your price, let's suppose you're having a t-shirt, so you're going to sell t-shirts for $5, then your revenue would equal the number of t-shirts that you sell, which would be X. So let's sell 10 t-shirts for $5. So notice you're just going to take 10, which is the number of t-shirts you have, times the $5, and that's going to be your revenue. So notice that all you have to do is multiply your price times X to get your revenue. So if your price continues to fluctuate along this function here, then to find the revenue, I'm going to take that function and take X times the function, 60,000 minus X over 20,000. So a little bit better look at the revenue would be, if I multiply that out, 60,000 X minus X squared over 20,000, which, keep in mind, is the same thing as negative 1 over 20,000 X squared plus 3X. So you could use any one of those equations, but that's my revenue. Keep in mind, this is my revenue because I'm going to be using this information in the next few moments, but I'm going to have to remember that the revenue is this amount. So to find the marginal revenue, I'll need to take the derivative of the revenue and evaluate it at 20,000. So I already found the revenue function, which was negative 1 over 20,000, which I'm going to be using in the last example here in just a moment. So let's go ahead and find the derivative of this and then evaluate it at 20,000. So again, the cheat method here is just to multiply. So negative 2 over 20,000 is negative 1 over 10,000 X plus 3. And then if I evaluate the revenue, which sometimes is denoted as dr over dx with respect to x. Now I'm going to evaluate r, the revenue, at 20,000. I'll get negative 20,000 over 10,000 plus 3, which is negative 1 plus 3. Let me try that again. I think that's a negative 2 plus 3, which is $1 per every unit. So that's the increase in revenue. I'm going to increase my revenue by $1 for every unit. So again, here's how the author chose to do it. This might have been a little bit more simple because we have just a constant, and then you could take the derivative here. Remember the constant rule for derivatives. So the author worked it out just a little bit differently. You're welcome to pause the video here and see his work, but he still ended up with $1. So the last example, example number 8, is probably the most complicated. You'll need to remember that the profit is equal to the revenue minus the cost. So they're going to give me a cost function here, and they're asking me to find the profit. So this is where I told you that you're going to have to remember what the revenue was back in example number 7, which I think was that -1 over 20,000 x squared plus 3x. And then I'm going to subtract off the cost, and then remember to distribute that negative. So this is the cost is this guy in pink, or this guy in blue. So that goes right here, and then I have to distribute that to every term. So here's the blue term that we were talking about. So again, students sometimes forget to distribute that to every term. So combining like terms, distributing, again, they use a little bit different form for the revenue. I had it simplified, but either way, we're going to get down to 2.44x minus x squared, and we're going to evaluate that at 20,000, 24, 400, and 30,000. But before we evaluate it, we need to find the derivative of P. So I'll go back. Here's my profit function. So this is where we had left you off. So let's go find the derivative of the profit. And again, this is a capital P, not the price. So the derivative of this thing is 2.44. The x wipes out. This is going to be, so you could think about this being 2.44x minus 1 over 20,000 x squared minus 5,000. Now the 5, when you take the derivative of the constant, it'll go away. But this 2 times the negative 1 over 20,000 will give me negative 1 over 10,000. But I have an x in there as well, so I'll just say x over 10,000. So the derivative of this became this red. So that's how they got to this point. And then once you have that derivative, you're just going to evaluate it at 20,000. Again, I'd use my calculator. You would evaluate it at 24,400 and evaluate it at 30,000. And I think here comes some answers. So 44 cents per unit, you're breaking even per unit. That's if you let X be 24,400. That's the number of t-shirts that you're selling in that example. And then you're in the hole per unit if you create too much. So you can see you want to maximize your profit. And 24,400, you're breaking even. And then at 30,000, you're actually losing money. I hope this video was helpful. If you have any questions, feel free to email me. Thanks.